sorry, I was doing the compliment. 9,
doing the compliment.
8, 7,
Okay.
6,
Wow.
5, 4, 3, 2, 1.
Excellent. Okay. Well, it is my great pleasure, given that this is a sporadic topology seminar for this term, to be introducing George Bar-Natan, who kindly offered to give a talk about the strongest genuinely computable not invariant 2024.
Okay. So, yeah, that's my title and abstract. I hope you read it. Thanks for allowing me at UBC. I wasn't invited, right? I invited myself, so you only allowed me. So thank you. I should add that everything is joined with Roland van der Veen, and here's what he looks like. And you hopefully all hold a copy of the handout. That's what it looks like. Also, everything is online, and you can scan this QR code or go to drobien.net/UBC24, which is also now defined to be omega epsilon beta. So when you see below URLs, they all start with this, and then you know what they are. I have to acknowledge my answer grant and a grant from the Chu Family Foundations in New York City, so thank you for your help. And my title has the word strongest genuinely computable in it, so I want to explain this word. So strongest is explained here. So the invariant is called theta, and it's actually a pair. Delta, which is just the old Alexander polynomial, and lowercase theta. And I've computed it on all nodes with up to 15 crossings. And for comparison, I've also computed it on the I've also computed the HOMFLY polynomial and Khovanov homology taken together. And the invariant that I talked about in Oaxaca, for example, and that I was talking about from 2022 to 24, so the ordered pair delta and rho 1, and also that one, okay? And then if you look up to 10 crossings, there are 249 nodes, and HOMFLY and Khovanov homology taken together take 248 distinct values, which means that there is a deficit of 1. Delta and rho 1 have a deficit of 0, and uppercase theta has a deficit of 0. And then if you start increasing the crossings, so if you look up to 11 crossings, there are 801 nodes. Khovanov and HOMFLY together have a deficit of 30. Theta has a deficit of 3, meaning it attains 798 distinct values. And if you go down to 15, there are 300,000 plus nodes, and by now I only wrote the deficits. So Khovanov and HOMFLY taken together have a deficit of 70,000. Theta has a deficit of 6,700. And if you combine everything together, you get a deficit of 6,000. So basically you don't gain a lot by combining everything together, but yet theta is roughly 10 times better than Khovanov and HOMFLY taken together, at least with this measurement, at least according to this measurement. Yes?
Can we briefly switch screens back to this? I need to make it so that PIMS is unmuted so that participants can hear it. I realize
so that's, you're asking me to do something that's here, not...
Yes. Oh, there we go. Now we're going to unmute this. Okay.
Wait, so is Dale out there?
Mihai is. And so maybe Mihai can hear now. How do I get rid of this echo?
You turn the volume down on the pad.
But it says it won't.
Wait, but...
Now is it? No, it won't let me do it.
Wait, what are you looking for? What are you trying
I'm
to
trying to
do?
make it so that my iPad doesn't create this echo.
So just mute it.
Yep.
Turn the volume to 0.
You would think
Could you
this is-
leave? You could leave the meeting. But that would be a fact.
What, make George the host and then I leave? Yeah. So you can switch your screen back. I'm going to make you the host. I'm gonna switch.
You can potentially also just leave the audio altogether on that device.
Well, I think we just do it this way.
Right. Sounds good.
And meeting still running.
So
Excellent.
just tell me when I should start.
You're good. Me, I can hear,
Okay,
and we're good.
okay, good. So, so that's what I mean by strongest. Yes?
Are there any theorems that say that you can get to zero in principle? Stronger invariant, it's a little
Not
vague.
while being genuinely computable. Okay, so yes, there are algorithms to separate knots, but they are very exponential. They're very, very, very slow. So if you also want to be able to work with large knots, then no. Then this is the best there is, or that's what I'm asserting. Okay? So now let me explain what I mean by genuinely computable. So, so theta is actually a pair of a single variable polynomial and a two variable polynomial. A single variable polynomial is just a list of numbers, and I can code them by drawing the positive numbers in red and the negative numbers in blue, and also make the shading proportional to the magnitude, the brightness proportional to the magnitude, and then I get a barcode. And the second component, theta, is a two-variable polynomial, and a two-variable polynomial is a two-dimensional array of numbers, so it codes a picture. So I like to think of it as a barcode and as a QR code. And then what you see here, the barcode and the QR code together, are the invariant of a certain random, roughly random, 300 crossing nodes. So in particular, I'm trying to tell you that you can compute theta on 300 crossing nodes. Yes, Itai?
Yeah, so again, so you're saying when it's brighter, that means the magnitude is bigger.
Yes,
so,
yes. So if it's
here-
kind of very light, so towards the edges, the magnitude is small, but the color encodes in the middle the magnitude seems to be big, and the color encodes only the sign.
Okay, so I wasn't sure if you were saying it was big in the corners or small in the corners.
Small
You
in
were
the
saying it's
corners.
Small in the corners.
Small in the
Okay.
corners. Small in absolute value in the corners.
Okay.
Anyway, the mere fact that you can compute it for 300 crossing nodes is science fiction for pretty much everything else in knot theory. Like the 300 crossings is way above imagination for practically anything, except the Alexander polynomial. Anyway, but I also want to assert that the invariant is fun. Basically the values are barcodes and QR codes are pictures. And the pictures seems to have patterns in them. For example, they're hexagons, and they seem to have on them what looks like sun table waves. Okay, so you put sand on a table and shake it, you get waves. So you get various weird patterns, and basically you can see these patterns, and almost every pattern that you will see, I don't know how to prove. So the fun is the pattern, and also the fact that we're going to spend a few years trying to understand them. Okay? So here are a few more pictures. Oh, this is the same picture a bit magnified. And here are knots with 50 to 73 crossings. So basically you see the same kind of patterns, and but for each knot they're slightly different. I don't know what that is. Okay? Here is the Rozansky table of knots. So the QR codes and the barcodes for the first 250 knots, because we also include the unknot on the upper left corner. And here are a few torus knots, again, just for fun. And here is one big torus knot, again, just for fun. And I think I rest my case about fun. But in addition, it's also meaningful. So with extremely high confidence, though yet without a proof, theta gives a genus bound. So there's something about like the degree of theta, the degree of the second component of theta is in lower bound, or divided by 2 is a lower bound for the genus, and it seems to be better than the Alexander polynomial alone for certain knots. Okay, and you'll see example later. And also, we hope, and there is reason to the hope, that theta will eventually be able to say something about ribbon knots, but that's a bit of a speculation right now. Basically, the point is that, you know what, I'll skip the point because I want to talk about theta and not about what it may or may not do in the future. But I should say also that there is a bad bit, or maybe it's bad, maybe it's good. I mean, that's, so the art of working with theta is a bit more like glass blowing than pottery, and mathematicians like pottery. So pottery, you know, you hold the material with your hands. Everything you do directly with your hands. If you try to do it with glass blowing, it will be quite bad for your hands. You always have to use tools, tongs or something. And what it means in the case of theta is that basically it's very computable, but for computers. For humans, the formulas are nasty. So even the smallest knots, you have to use tools to compute. Okay? So that's what I mean by the bad. Anyway, long time ago, Von Jones told me that formulas stay and theories change with time. So rather than telling you about, stories and theories, I'll tell you the formulas right at the start, okay? And there is actually also a reason to it, because the truth is that I don't believe in our theories. The theories led to theta, but I believe that these formulas ought to have simpler explanations. So in some sense, the formulas are more valuable than the theories, okay? Anyway, here are the formulas. Here is how you compute theta. So, given an n crossing knot, you draw it you cut it open and you draw it as a long knot, and it doesn't matter where you cut it open. And then you draw it in such a way that all the crossings are with both strands facing up. And of course you can do it, because if you have a crossing in which the strands are not facing up, you just turn it around a little bit, and then all the strands are facing up. And then you label the diagram with the edges of the diagram with 2 numbers. So one number is a running index, so 1, 2, 3, 4, 5, 6, 7. And the other number is the rotation number of the edge. So each edge starts pointing up and ends pointing up, because I drew things in such a way that all edges are, that at the crossings everything is pointing up, and also at the beginning and at the end. So each edge starts pointing up and ends pointing up, and then if you follow the tangent vector to the edge, it may rotate, and you let phi k be the rotation number of edge number k. So for most edges here it is 0, so this edge does not rotate, this edge does not rotate, this edge does not rotate. However, edge number 4 starts pointing up, ends pointing up, but in between the tangent does one rotation clockwise, so phi 4, the rotation number of edge number 4, is -1. Okay? And then, so this is just setup. This is how you draw the knot so that you'd be able to compute its theta, its invariant. And then you let A be the 2n plus 1 by 2n plus 1 matrix. So if the knot has n crossings, it will have 2n plus 1 edges. And then I let A be the 2n plus 1 matrix by 2n plus 1 matrix that you get by starting from the identity matrix. And then for each crossing, you add a 2 by 2 block to the matrix as follows. So basically, a crossing is a triple of numbers. It's the index of the upper strand. So always I call it I. The index of the lower strand, incoming, and then the outgoing upper strand will be I plus 1, and the outgoing lower strand will be J plus 1. So it's the indices of these two strands and a sign for whether the crossing is positive or negative. So each crossing is 3 numbers, S, I, and J. And then corresponding to any crossing, I will add to the matrix S in row I and row J, and column I plus 1 and column J plus 1, the 2 by 2 block written here. So negative T to the S minus 1, 0, and minus 1. Okay? Again, I'm doing unexplained formulas right now. Okay, that's kind of what I promised to do. So for example, for the trefoil knot shown here, the matrix you get is the identity on the diagonal. And then for the yellow crossing, so the yellow crossing has I equals 6 and I equals 3 and J equals 6. So in rows 3 and 6 and in columns 4 and 7, I add entries as written here, so you get these yellow entries. And likewise, for the pink crossing, you get the pink entries. For the bluish crossing, you get the bluish entries, and that's the matrix A. Okay? Then I let G, whose entries I call G alpha beta, so it's an array of numbers, be the inverse of A. So for the trefoil example, well, we just saw what A is, and G comes out by inverting A. This, by the way, is the bottleneck of the computation. So inverting a matrix using row reduction, whatever, is a polynomial time computation, and but still it's a hard one, and that's where all the complexity is. Everything else, everything that follows is easier computationally, even if the formulas are complicated. Okay? And by the way, the entries of this matrix I call the green function. So the G alpha beta up there is also the called the green function. Okay? And if you are, maybe you should, okay, if you are a classical topologist, you should be saying that this is boring and you should yawn and fall asleep. Okay? Because indeed, the 2 by 2 matrix should remind you of the Bureau representation. The matrix A altogether is a presentation matrix for the Alexander module of the knot, computed using Fox calculus on the Wirtinger presentation, and even its inverse G is related to the so-called Blanchfield pairing. So all of this is classical, and in particular, the Alexander polynomial up to a normalization is the determinant of A, and the normalization is you have to multiply it by a unit, so by t to some power, and the power is the negative of the total rotation number of the diagram minus the total right of the diagram divided by 2, where the right is the sum of the signs. Okay, but all of this is classical, and you should be thinking it's boring. The new stuff starts here. So I let T1 and T2 be two indeterminants, two new variables, and I let T3 be the product of these two. And then for nu equals 1, 2, or 3, corresponding to the 3 variables, I let delta sub nu and g sub nu, which is basically now an array depending on 3 things, so nu and alpha and beta. So these are delta and g subject to the substitution. Instead of t, you write t sub nu. So basically, delta 1 is the Alexander polynomial at t1. Delta 2 is the Alexander polynomial at t2, and so on. And likewise, G is the inverse matrix of that matrix A, but the matrix A depended only on T, so G1 will be the same matrix with T1, G2 will be the same matrix with G2, and G3 with T2, and G3 will be the same matrix with T3. And then I let theta of K be delta 1, delta 2, delta 3, that's just a normalization, it's not interesting, plus a summation over all the crossings of some functional R1 that depends only on the crossing, on a single crossing, plus a summation on pairs of crossings, C0 and C1, of a functional that depends on 2 crossings, so theta of C0 and C1, plus another renormalization normalization thing, which is a summation over the edges of some functionals that depends on the rotation number of the edge and just the number of the edge. All of these things are extremely easy to compute. The formulas are complicated, but basically R1 of C is something quadratic in the entries of G, of the matrix G, and the quadratic in the green function. Theta is something cubic in the green function, and gamma 1 is actually something linear in the green function. And so all of these computations are really very, very easy. A double summation on a knot with 300 crossings is just a summation over 300 squared terms. This is something that a computer can do very easily. Okay? But I still have to tell you what are R1 and theta and gamma 1, and this is where things get ugly. So the simplest formula we could find for R1 is the one written here. So it's something quadratic in the G elements, in the elements of in the green function, with some coefficients which are simple-minded polynomials or rational functions in T1, T2, and T3. Likewise, theta is something cubic in the green function. So here it's a product of 2 green functions, but then that gets multiplied by another one. Okay? So theta is something cubic in the green function, and gamma 1 is, again, something linear in the green function. So again, you can look at it and say, this is ugly, this is disgusting, the formulas are horrible, but from a computational perspective, these formulas are very, very, very easy. And all that there is to computing the invariant is inverting a matrix, and then a double summation over the crossings of this simple formula. And also a single summation, but that's even easier. Okay? So again, from a human perspective, it's extremely ugly, but from a computational perspective, it's extremely efficient. Okay? Anyway, theorem, theta, so this quantity, this odd, or this funny sum that I wrote, is a not invariant, and therefore the pair delta and theta, which I call uppercase theta, is also a not invariant. Okay? You with me? Good. Now, you see, I take the Jones thing about formulas and I generalize it even further. So for me, formulas don't mean anything unless they're implemented, unless they actually run on a computer. So let me show you an implementation. So here is a complete implementation. Well, first of all, there are preliminaries. I load some packages that don't do much. So one package is just an enumeration of knots. Another package is a package to compute the rotation number of edges. It's actually a bit difficult to compute the rotation number of the edges from the standard presentation of a knot. Combinatorially complicated. I can say by hand how you do it. You draw the knot in a certain way and then you trace with your finger. But if you want to do it on a computer, you need a little package and it's completely besides the point. So I'm loading it and I'm not showing you how it works. And the last package that I'm loading is polyplot.m, and all that one does is to plot one variable polynomials as barcodes and two variable polynomials as QR codes. So that's just to make the results look pretty. So I'm loading all of these three packages, and then the real program starts. So forget this. This is a technicality. This is how I want to simplify certain things. Then I set T3 to be T1 times T2, and I define R1 to be this. This is precisely the R1 that was shown in the previous blackboard. And if there is some disagreement between them, this is right and the previous blackboard is wrong, because the previous blackboard I typeset in tech, and this one actually runs and produces correct results. Okay? Then likewise, here is lowercase theta, so it's a function of two crossings. So one crossing is denoted S0, I0, J0. The second crossing has S1, I1, J1. So the sign, the index of the upper strand, the index of the lower strand, and likewise for the second crossing. And again, this is the formula. And if you and if it disagrees with the printed formula, this is the right one. And finally, this is gamma 1. And then here is the program. This is the whole program. After you've put in the data, this is the whole program. So you let C's, so C's is the list of crossings, and phi, the list of rotation numbers, be rot of k, where k is the knot. So rot computes that, I don't care how. Then n is the length of C's, so the number of crossings. Then A is the identity matrix, and then for each time you see an Sij inside the list of crossings, you take A at rows I and j and columns I plus 1 and j plus 1 and add to it this 2 by 2 block. Then you let delta be the determinant of A, normalized by exactly what I said it should be. And then geval is just forget, it's evaluating the green functions, but basically the main point is that you let Z be the double sum of the theta of pairs of crossings, and then you add to it a single sum over the crossings of R1 on each crossing, and then you add to it the rotation number corrections, and then you output the pair, the Alexander polynomial, and delta 1, delta 2, delta 3 multiplied by Z, and I factor everything because I like the results factored. Okay? That's all. That's the whole program. And it literally does what the mathematics was. You can read it. It reads exactly the same as the mathematics. Anyway, here it is running. So here is theta of the knot 3,1, so the trefoil knot. So first of all, this is the Alexander polynomial, and this is the new component, okay, the second component, lowercase theta, and it's a two-variable polynomial in T1 and T2, because remember that T3 is just T1 times T2, okay? And then I ask my computer to plot this, the theta of the knot 3,1, and in addition I add the Conway knot and the Kinoshita-Terasaka knot. So two famous 11 crossing knots. And then what do I have to tell you? So first of all, so I think I already explained how to read the barcodes, but let me explain how to read the QR codes. So I'm plotting, but I'm plotting in a funny way. So basically, this is the coefficient of T1 to the 0 T2 to the 0. It's white because this coefficient is 0. And then if I move 1 unit to the right, it increases T1 by 1. And if I move 2 units to the right, it increases the power of T1 by 2. And so this blue hexagon here means that the coefficient of T1 squared is negative. And if we look at the actual polynomial, here, T1 squared, where is T1 squared? Here. T1, no.
There was,
Oh, here. T1 squared has a negative coefficient. And then for T2, instead of making it a rectangular system, so T2 goes in this direction. So the direction of the cubic root of 1. So this will be, this hexagon corresponds to T2, and this corresponds to T2 squared, and hopefully T2 squared is also, the coefficient of T2 squared is also negative. But then if you go 1 unit to the right, this will be the coefficient of T1, T2 squared, and that should be positive. Let's check that. So T1, T2 squared has a positive coefficient. Okay, I'm just explaining how the pictures correspond to the polynomial. And then the reason I'm showing the Conway knot and the Kinoshita-Terasaka knot is because these are notoriously difficult to tell apart. And indeed, their barcodes are the same. Their Alexander polynomials are the same, and in fact, both of them are just 1, because it's only 1 bar and it's red. Okay? But their theta is different. And in fact, as I mentioned, the degree of theta is related to the genus, and indeed, well, here there are many more hexagons than here, and indeed, the hexagon of the the genus of the Conway knot is bigger than the genus of the Kinoshita-Terasaka knot. I just realized that I'm confusing words. I'm like switching words in my mind, and this has to do with the fact that I landed in Vancouver at 1 a.m. yesterday. Sorry, no, I got home at 1 a.m. So please stop me if I become incoherent. Okay? Anyway, again, just for fun, I'm letting the computer compute these torus knots that I've shown you before, but now you know what it means. Okay, so this is the torus knot 13.2. It's a rather small one, only 13 crossings, but the invariant is written here. So, well, I don't know what to say. These are the values. And then it gets more and more fun the more interesting the torus knot is. And I, again, don't want to say more about it. I want to start with the stories part of the talk. Is this okay so far?
what do you, for the genus, what are you measuring? Just the width, just the...
The degree in T1, which is the same as, which is conjecturally the same as the degree in T2. Because I remind you that all the patterns that you see, I actually don't know how to prove.
Right, so like even the symmetry?
Even the symmetry.
Okay.
Okay.
So how do you prove that the state is an invariant?
Oh, I will prove that it is an invariant in a few minutes. In fact, I'm starting to prove that it is an invariant right now. So I promised to tell you stories, so let me tell you about how cars drive on knots. So first of all, knots are oriented pieces of road, and cars only drive following the orientation. They only drive in the orientation of the knot. Okay? So they always drive forward. When a car passes under a bridge, so an interchange, it goes through with probability 1. So basically here, if the car enters on the understrand, it will come out with probability 1 on the other side. However, if the car enters with, on the upper strand than with probability t, where t is, you think of it as a number close to 1. So almost always it will come out, it will just continue. But then with a small probability, the probability of the probability 1 minus t, it will fall from the bridge and it will continue driving happily on the lower strand. One way to say it is to say that if you put, what are they called, traffic counters, so you know these black rubber things that they put on roads to count traffic. So if you put a traffic counter, so if you inject the traffic here and you put a counter here and a counter here, this counter will measure t and this counter will measure 1 minus t. This is for positive crossings. For negative crossings, it's exactly the same, except t gets replaced by t inverse. So if you're on the understrand, then this traffic, if you inject the traffic on the understrand, then this counter will measure 1 and this counter will measure 0. And if you inject the traffic on the upper strand, then this counter will measure t inverse and this counter will measure 1 minus t inverse. And now you can complain that this really isn't probability theory because t and t inverse cannot both be between 0 and 1 at the same time. They cannot be probabilities at the same time. I don't care. I treat algebraic, I treat probability theory algebraically. Like the probability of the product is, of an intersection is the product, the probability. So I use the algebraic rules of probability without interpreting them as numbers between 0 and 1. By the way, quantum mechanics does more or less the same. Okay? And then the last traffic rule is that when the car comes to the end of the knot, it falls off the cliff and disappears. Okay? So, theorem. You know what, even before the theorem, theorem, the green function g alpha beta that I defined before is the measurement that a counter placed on edge beta will measure if you inject traffic on edge alpha. And there is a little bit of ambiguity if alpha is equal to beta. So the convention is that if the counter and the injection point of traffic are the same, then the injection point is before the counter. Okay? So for example, let's analyze traffic on a kink. Okay? So if I inject traffic on edge number 1, and I measure traffic on edge number 1, since the measuring point is right after where I inject the car, the measurement will be 1. If I still inject the traffic on edge number 1, but now I want to measure the traffic on edge 2. So how will I get traffic on edge number 2? Well, the car could go here, or the stream, the traffic stream, could go under the crossing, so it goes unchanged, and I measure 1. But then I would want to continue, but 1 minus t of the traffic will fall down and will get measured a second time. And then 1 minus t of that will fall down a second time and will get measured a third time, the third time. And then 1 minus t of that will fall a third time, basically. So you get a geometric sum. And the counter placed here will measure the sum over all p's, where p is the number of times you dropped down, of 1 minus t to the p. And again, this is a geometric series, and it comes out to be t minus 1, t to the inverse, t to the minus 1, t inverse. Okay, I really am not coherent today. And finally, what will this counter measure? So all cars at the end exit before falling. So this counter will measure 1. Okay? And now, what if I inject the traffic on edge number 2? Then the counter on edge number 1 will measure 0. For the counter on edge number 2, nothing has changed. Basically, if I inject here or I inject here, it's the same from the perspective of this one. So it still measures t minus 1, and t inverse, and likewise for edge number 3, nothing changed. And finally, if I inject the traffic on edge number 3, then no traffic will ever come to edges number 1 and 2 because they're behind. But on edge number 3, I will be measuring 1. So I claim that the green function computed by the rules of before will be 1 t inverse 1, the matrix, 1 t inverse 1, 0 t inverse 1, 0, 0, 1, namely the matrix written here. Okay? So, proof. So again, I have to show you the equality of two quantities, like the G alpha beta measuring traffic, and G alpha beta, the other G alpha beta, which is the inverse of the matrix A. So I will tell you that near each of the crossings, so if you're looking near a crossing, let's say a positive crossing, whose upper strand is I and lower strand is J, then both quantities satisfy the same G rules, where the G rules are written here. So let me explain what they say. So for the G, which measures traffic, I'm asserting that if you inject the traffic on edge J and measure it in position beta, where beta is somewhere else, then you get the same as if you inject the traffic in position J plus 1 and measure at the same beta. But that's the rule that says that cars go undisturbed under a bridge. If you inject the traffic at J, or if you inject it at J plus 1, it's exactly the same, except if you are measuring, if the place where you're measuring is between the two places, namely if you're measuring right here. If you're measuring right here, there is a difference, and the difference is a delta function. It's the delta of J and beta. So if beta is equal to J itself, you get a difference. Likewise, the second G rule says that if you inject at I, then that's the same as t to the power s times injecting at I plus 1, plus 1 minus t to the power s injecting at J plus 1. That's the rule about falling from cliffs. If you inject at I, it's the same as t times injecting at I plus 1, or 1 minus t times injecting at J plus 1. But there is only one exception. If the exception is if the measurement point is at I. So there is a delta function exception if the measurement point is at I plus 1, if it's here. Why is it at I plus 1? Sorry, no. Sorry, at I. It's delta IB. I beta. Sorry, I really am unfocused. Okay? Sorry about that. But on the other hand, if you expand what A times G is equal to the identity, so G is also the inverse of A. If you expand A times G, if you look at what A times G equals to the identity is, it's exactly the same two rules. And these two rules you can show determine G, and therefore the two G's, the G of measuring traffic and the G of the inverse of A, are the same. But you get a little bonus from this, And this is, you see, if A times G is equal to the identity, then G times A is also equal to the identity. And this gives you rules for how to move the injection point. And the equation G times A is equal to the identity gives you rules how to move the traffic counters. And if you expand G times A, the rules you get are that G alpha I, so if you are measuring at position I and injecting anywhere you want, then that's the same as measuring at position I plus 1 and injecting anywhere you want with some delta function correction and with some coefficient, and likewise for the second. So basically you can push the counter, a counter from I to I plus 1 and from J to some combination of I plus 1 and J plus 1. Okay? So this is preliminary. And now let's start the proof. So I want to show you the invariance of this quantity theta. Let's do the hardest bit. So to show invariance, I need to show invariance under the 3 Reidemeister moves. And in fact, since my notes also care about rotation numbers, there are like 5 Reidemeister moves or so, because you also have to care about how rotation numbers interact with the usual things. But Reidemeister 3 remains unchanged, and it's the hardest. So I want to tell you how the invariant changes under a Reidemeister 3 move, and here is a Reidemeister 3 move. Okay? So the left-hand side is one side of the Reidemeister 3 move, and the right-hand side is the other side. Okay? So suppose I inject the traffic on the lower left. Well, with probability t, or a counter placed here will measure t, and then it will continue here, and a counter placed here will measure t squared. A counter measured here, the only way a car could get here is if it went up and then it fell down. So it will measure t, and then t times the probability of dropping, so t times 1 minus t. And finally, the only way to get here is to drop down here, so a counter placed here will measure 1 minus t. On the right-hand side, if I inject the traffic on the lower left, then actually I have two ways to get to the top left. I could either drop down, and that happens with probability minus 1 minus t, and then continue and drop down again, so it happens with probability 1 minus t squared. Or I could continue, and this happens with probability t, and then drop down, and that happens with probability t times 1 minus t, and then flow under the crossing, so that happens with probability 1, so I'll get t times 1 minus t. And if you compare what's written here with what's written here, then you can simplify and you find that they're the same. And likewise, what's written here is the same as what's written here, and what's written here is the same as what's written here, and the same will be true if you inject the traffic here or here. And the conclusion is that performing Reidemeister moves does not change the overall traffic patterns. So it does not, so inside this picture, things have changed. So the edges are not the same edges. This edge has a t in it, I don't know. Well, no edge here has t times 1 minus t, like this edge. So the inside the picture, things change. But outside of the region of the Reidemeister move, it doesn't matter where you enter, you'll exit with the same probabilities on the upper side, whether you're on the left or on the right. Okay? So it follows that in the summation that makes up theta, so theta is a summation of various, or a double summation of various green functions that are computed near the crossings in which that appear in the summation. Okay? So theta does not change unless the summands that I care about, the summands that I'm computing, are within the region of the Reidemeister 3 move. So unless the summands contain in them G at I plus or K plus or J plus, that's a short for I plus 1 or J plus 1 or K plus 1. Okay? So what I do is I do the following. So first of all, sorry. And furthermore, if I want to know how the summations corresponding to the inner to the inner bits are changing, or if I want to understand these summations, well, I have rules. So these summations will involve alpha and beta, so injection point and traffic counters that are inside the diagram. But I have rules that allow me, that tell me how to move the injection point and how to rewrite G's such that the injection point will be moving up or the traffic counter will be moving up. So I can rewrite whatever I get here using the variables, using the injection point and the traffic counters at the top. And likewise, I can do it for here. And then the G's are the same. So I just have to check that the sums themselves are the same. So let's do it. So I first of all define the G rule. So GR stands for G rules. And the G rule corresponding to a sign S, so to a crossing. So to a crossing with sign S and index and upper index I and lower index J, or upper strand I and lower strand J, is the, these are the G rules that I copied from above. Okay? And then I define the diagram sum, so the sum corresponding to a list of crossings to be exactly the sum written in the definition of theta. So it's the sum over all crossings in this list of R1 of the crossing. So it's the sum over all C's of R1 of the crossing, plus the sum over all pairs of crossings. C0 runs over the crossings, and C1 runs over the crossings of theta of C0 and C1. And here all the rotation numbers are 0, so I don't care about them. And then I compute the diagram sum for the left-hand side. So the left-hand side has 3 crossings. A crossing with sign 1 between strands J and K. So this is this one. A crossings with sign 1 between strands I and K plus. So this is the second one. And the third one is the third one, and I can't reach it anyway. And I apply to this sum the G rules. Likewise, the right-hand side is the summation corresponding to the 3 crossings on the left-hand side, on the right-hand side. And to this, I apply the G rules of the right-hand side. Now, you can complain that I may have a double, so part of the invariant is defined by a double summation. And in a double summation, things could fail if one of the crossings in the double summation is inside the region of the Reidemeister 3. Okay? So I've added a fourth imaginary crossings to both sides, and it's the crossing between strands M and N. It's somewhere else. and I include it in the summation. So the list of crossings also include a fourth crossing, both here and here. And then this will capture the case where one leg of the theta, one leg of the double summation falls outside of the picture. Anyway, I compute the left-hand side, compute the right-hand side, ask the computer to simplify whether they're equal, and the simplified version of this equation is true, which means the two sides are equal, which means I've proven invariance under Reidemeister 3. So I don't know if you followed me. I might be a bit incoherent, and I have my excuses. But whether or not, I hope you followed me, but this is a complete proof. Okay?
I missed the step where you introduce additional variables.
So
I
basically,
followed the part was T.
so basically, so if you have a complicated knot, the invariant is a double summation. So I pick two crossings, and I compute something that has to do with the traffic around each one and the traffic between the two. Okay, so that's what the invariant computes. Okay?
So it's like
now,
a pair of counters?
What?
It's like a pair of counters?
Yeah, so I basically, the invariant is some cubic function in the, or the summand corresponding to this pair of crossings will be some cubic function in the G alpha beta. So basically I inject cars here and measure them here, times I inject car here and measure them there, plus times I inject car somewhere else and measure them there, all with some coefficients.
And the condition
Okay.
that the product
And-
of T1 and T2 is T3? How,
So this is just a, so the car, so in fact there are three types of cars. Cars that drive using T1 rules, and cars that drive using T2 rules, and cars that drive using T3 rules. And T3 just happens to be T1 times T2. Okay? And then suppose I want to show that the summation corresponding to this is equal to the summation corresponding to that. So I need to check what happens if basically the two crossings are inside here, or one of the crossings is inside here and another one is outside. Okay? So I added the extra crossing, the MN crossing. So the MN crossing, I've added it completely generically. M and N are not related to I and J. So they could be anything. So this is any extra crossing. So for any extra crossing, I'm doing the double sum in which I look at any pair of crossings between these three and the extra one. And that includes the cases where the two crossings in the double sum are inside here, but also the case where one of the crossings in the double sum is here and one is here. So adding this extra crossing just covers all the cases. And this is it, that proves the invariance. So the other Reidemeister moves, oops, what happened? The other Reidemeister moves are proven in a similar way. And this is it, that's the end of the proof of invariance. Maybe the most important part of the talk is the questions, and I don't really have time for them, but very briefly, so there are similar invariants, but much less computable. So invariants with similar properties but much, much less computable. So they're computable in exponential time. In work of Garoufalidis and Kashayev, and I don't know what's the relationship. Two, I don't even know that the value is also always have a hexagonal symmetry. It seems that they do, but I don't even know it. I wish I had time to tell you how to relate theta with quantum algebra. So in fact, it came from quantum algebra, but strictly speaking, quantum algebra only gave us the inspiration, not the formulas. So I actually don't know that theta is the quantum algebra invariant. Theta also seems to be equal to something called the two-loop contribution to the Kontsevich integral, but again, I don't know it. I'm only conjecturing it. It's definitely true, but strictly speaking, no proof is written. I think I'll skip the integral formulas, but I'll just tell you, maybe I'll skip to dream number 9. So so where is it coming from? Okay, so you can look back at the conjectures and say, oh, it's coming from finite type theory, or it's coming from quantum algebra. But both of these explanations are way, way, way harder than the end result. So there ought to be an explanation of these invariants by terms that are much less foreign. And I don't know that explanation. So, and maybe I'll stop here. So, yeah. I'm sorry about
No problem. Other questions?
So did you use computers to sort of half guess the invariant and then check it, or did you write down the invariant
No,
and then use the computer to check it?
So quantum algebra told us that there should be an invariant with basically things like that, which is a double summation which is a sum of 3 terms, one of which is a summation over the crossings, another is a double summation over the crossings, another one is a summation over the rotation numbers, and furthermore, it told us that R1 should be quadratic in the G's, theta should be cubic in the G's, and in fact there is a little bit more that comes in here. If you look, well, okay, I will not show it, but there is some weights that are preserved. So quantum algebra told us in which space of formulas to look for, and then we just looked for the formulas by undetermined coefficients.
So for that, you use a computer, or you did it by
Yes,
hand?
of course. Everything is with tools,
Okay.
right? It's glass blowing, it's not pottery.
And the quantum group you said is SL3 somehow, or you
Yeah,
saying-
so the quantum group here is SL3, yes.
So there should be something else for SL4, or
So there should
No,
be,
or SL2?
yes, so in fact, one of the statements I made there is that there should be many more invariants like that. It's possible, so basically, the more complex, so if you make the group larger or the power of epsilon larger, the summation becomes more complicated. So at the moment, it's a double sum of something that's constructed out of the inverse of a matrix, and inverting the matrix is harder than computing the double sum. If I'll switch to a higher power of epsilon, whatever epsilon is, then it will become triple summation and then quadruple summation, and then at some point doing the multiple summation will become harder than inverting the matrix. So at some point these invariants will get less and less efficient. So there is still room for one or two invariants that are stronger than theta and that compute at roughly the same amount of time. And then after that, it will stop.
But the epsilon you're saying is related to the SL3, the 3 in the SL3? Is that
No, there is another parameter.
Okay.
It's related to Q of the one. No, it's actually not. It's another parameter.
Okay.
But the three. So if you switch to 4, you'll get nothing new, unless you also increase the power of epsilon. So like the next interesting invariant will be SL3 at epsilon squared. And that's, at the moment, still too hard.
And the SL2 case is somehow trivial? Or?
SL2 is what I called row 1. So that was the best there was between 2022 and 2024.
And this explanation with the probabilities,
Yeah.
did that come out of the theory also, or is it only
No.
after the fact? Once
It's
you-
after the fact. Yes?
What gave you the idea to plot the two-variable polynomial in this hexagonal way?
The root system, it all comes from SL3 somehow.
Right, fair enough.
Yeah, yeah, again, I apologize. I should have gone over my notes instead of going to lunch. I'm sorry.
No, lunch was good too. I think
Yeah.
that was a great talk. You should thank George.
Oh, okay.
Sorry, I didn't mean to cut you off.
That's okay. So the barcodes, is that the Alexander
Yeah, the
polynomial?
barcodes are just Alexander polynomial.
And
The QR codes are the
the
epsilon to the power 1 SL3 invariant.
is there a way to like obtain the Alexander polynomial from your QR code?
So if you look very carefully, you'll find that, well, for example, let's look at the torus knots. You'll find that the barcode is almost always equal to the top row of the QR code. So this is this is equal to that. This barcode is equal to the top row of the barcode. This is one of these observed patterns that we cannot prove.
Okay.
Okay? However, it's only almost always true, not always true. So there's clearly something there, but we don't know what that something is.
Thanks.
The cases where it's not true, are they interesting in some way? Like, do you know, yeah, they're not.
I don't know.
Yeah, they are interesting.
Sometimes it seems to be the reverse, like the negative.
There's a.
Oh yes, sorry, up to a sign. So in fact, what seems to be the case is that the top row here is a multiple of the Alexander polynomial, and this multiple is sometimes 0, and then you just don't see the top row. So, okay, but I don't know what that multiple. This is true by inspection, but I didn't have time to check what is the multiple. But you know, maybe the talk wasn't fun, but the invariant is fun, and if you play with it, you'll find things, and that's one of them, and then you can prove them, and I have no idea how to prove them.
Do you think because of this?
If you try to distinguish knots using just a small theta,
Yeah.
do you distinguish less than if you throw in the first components?
Of course, yes. So indeed, you know,
So
if
it
you
sounds
simply
like the
look
first
at
component could almost be extracted from the second one.
no, because for example, all of these have theta equal to 0. And the Alexander polynomial saves the day. And in fact, if you look at these two, this is 817 and 818, the QR codes are empty, the barcode appear the same, but that's only because I'm plotting only the signs and the approximate. But basically, if your eyes were better at detecting color differences, you'll see that the colors here are slightly different from the colors there.
So the coefficients are different.
So yeah, the actual the signs of the coefficients are the same, but the coefficients are actually different.
There's a question on Zoom from Mihai, but since you're the host, can you maybe tell Mihai to unmute?
Hi, unfortunately I
Jump
can't
to
hear the
latest.
audio.
No,
Oh,
that
this
was
was.
fixed. We fixed that. Jump to the, there we go.
Oh, okay. Did you say that the QR code says something about genera of knots? Yes. So basically the distance from the center, no, the degree in T1 or in T2, because they appear to be the same, is if you divide it by 2, and that's in a lower bound for the genus. And that lower bound is sometimes better than the lower bound that you get from the Alexander polynomial. As shown, for example for the Conway and the Kinoshita-Terasaka knots. Okay. Okay.
It's awesome. Great as ever. Thanks again, Brad.
Okay.